Hello. So this is my last video for this class. Gonna be solving a couple of Applied Linear Algebra 2 problems. We're going to be finding the saddle point of a matrix game, computing the expected payoff, and optimizing using the simplex method. For problem 1, they want us to find a saddle point for the matrix game having payoff matrix, and this is the given matrix. So we know that the saddle point is the minimum of row I and the maximum of column J. And so we're just gonna break that apart. Our first step is find the minimum value, Aij, of each row. So we look at each row individually, find the minimum value. The minimum value of row 1 is 3, because we have 5, 3, 4, and 3. The minimum value is 3. So I highlighted them, wrote it off to the side. Moving on to the second row, the minimum value out of -2, 1, -5, and 2 is -5. So I wrote it there. And then our last row, we have 4, 3, 7, and 3. The minimum value is 3. So I highlighted them. Now moving on to step 2, we are finding the maximum value, Aij, for each column, starting with our first column. Out of 5, -2, 4, our maximum value is 5. So we highlighted it. Our second column is we have 3, 1, 3. Our maximum value is 3. Highlighted them, wrote it down here. For our third column, we have 4, -5, and 7. The greatest value is 7. And then for our fourth column, we have 3, 2, 3. Our maximum value there is 3. And so, as we stated above, the saddle points are the minimums of the rows and the maximum of the column. So it's basically where these two are going to intersect, where they overlap, rather. So we can see here, the first row, we had these two minimum values, 3 and 3. And then when we look at those columns, they're also the greatest value of those columns. So those are our saddle points. 3, it is the minimum of the first row, and also the maximum of the second column. Same with all these other ones. So there are 4 saddle points in total, and to write it out, it's A, and then the row and the column. You can also write it like this, row, comma, column. So for our first one, we have A12 equals 3. So that's our first row and second column. First row, second column, we have 3. So you can write it A12 equals 3, or you can write it like this. It's at 1, 2. Our second saddle point is the first row and the fourth column. It equals 3. First row, fourth column, 3. So 1, comma 4. Our third saddle point is the third row and the second column. 1, 2, 3. Third column, or third row, second column is right here. And then our final saddle point is A3, 4 equals 3. So third row, fourth column, right here. So those are our saddle points. Pretty easy, pretty straightforward. Now on to our next question. Not that one. This one, yes. Problem number 2. We let M be the matrix game having payoff matrix. M equals 1, 2, -2, 0, 1, 4, 3, -1, 1. Find the expected payoff E of xy, v of x, and v of y when we're given these two situations, A and B. So the first one is when x equals 1/3, 1/2, 1/6, and y equals 1/4, 1/2, 1/4. And then for B, it's when x equals 1/4, 1/2, 1/4, and y equals 1/2, 1/4, 1/4. So starting with A, we're going to compute the expected payoff. So we're computing E of xy, and it's pretty straightforward. We're just going to be doing x transpose times m times y. And now we're given x, we're given y, and we're given m. We just need to compute x transpose, and then we can just start multiplying these matrices. So x transpose, we just make the column into a row. So We only have one column, so it becomes one row. So 1/3, 1/2, 1/6. And now we can start multiplying. So this is x transpose times m times y. And I like to just break it up a little bit. So I'm going to do x transpose times m first and find that. And then I'm going to multiply it by y. So we can see x transpose is a 1/3 and m is a 3/3. And the inside values match the 3 and the 3. So what we're going to get is a 1/3. So I got 5/6, 1, and 3/2. This is the product of x transpose times m. And then bring the y down here. It's going to be x transpose times m times y. This is a 1/3 times a 3/1. The insides match. We're going to get the outside, so we're going to get a 1/1. When we multiply these together, we get 13/12. So this is e of xy equals 13/12, the expected payoff. Next, we're computing v of x. This is the minimum value of x transpose times m, because we're trying to minimize the column's losses. So x transpose times m, we did that up here. This was x transpose times m. We got 5/6, 1, 3/2. So I just brought it down. And so we just choose the minimum value. We have 5/6, 1, 3/2. 5/6 is less than 1. 3/2 is greater than 1. This is 1. This is our smallest value. So v of x equals 5/6. And then this third step of part A is computing v of y. This is the maximum value of m times y. We are trying to maximize the row's winnings. So m times y, this was m, this is y. It's a 3/3 times a 3/1. The 3's inside match, so we're going to get a 3/1. So we get 3/4, 3/2, 1/2. And we're choosing the greatest value of all of these. So we have 3/4 is less than 1, 1/2 is less than 1, but 3/2 is greater than 1. So that's what our answer. So we have v of y equals 3/2. So that was part A. And now on to part B. We're just going to do that over again, but with the new x and y that they gave us. M is still the same though. So they gave us x, they gave us m, they gave us y. We just need to calculate x transpose first to be able to solve for the expected payoff, to solve for e of xy. So you just take the column of x and make it into a row. So the 1/4, 1/2, and 1/4. Now we can start computing. So remember from above, e of xy equals x transpose times m times y. This is it, x transpose times m times y, but I'm just going to do x transpose times m first and then bring the y down after. So x transpose times m, that's a 1/3 times a 3/3. We're going to get a 1/3. So we have 1, 3/4, 7/4, and then times m, or times y rather, bring it down. It's a 1/3 times a 3/1, so we're going to get a 1/1. And we get 9/8. So e of xy equals 9/8. That's the expected payoff. For step 2, computing v of x, remember this is the minimum value of x transpose times m. We're trying to minimize the column player's losses. So x transpose times m, we did that above in the first part. 1/4, 1/2, 1/4 times m. X transpose times m, so it's a 1/3 times a 3/3. We're going to get a 1/3. And we end up getting 1, 3/4, 7/4. We want to find the minimum value. So looking at them, 7/4, that's greater than 1. 3/4, that's less than 1. And then 1 is 1. So 3/4 is our answer. V of x equals 3/4. And then finally, computing v of y. Excuse me. The maximum value of m times y is v of y. So maximizing the row player's winnings, we do m times y. This is a 3/3 times a 3/1, so we're going to get a 3/1. we get 1/2, 5/4, 3/2, and we're trying to maximize, so we choose the greatest value. We have 1/2, 5/4, 3/2. 1/2 is less than 1, 5/4 is greater than 1, 3/2 is also greater than 1. So between 5/4 and 3/2, 3/2 is greater because that's 1 and 1/2, whereas the other one is 1 and 1/4, and 1/4 is less than 1/2. So 3/2 is our answer here. So we have v of y equals 3/2. So that was it for that problem. Now, on to our final one, which is simplex. Woo! We are going to use the simplex method. They want us to minimize the function given 2x1 plus 3x2 plus 3x3 subject to these constraints. However, we only know how to maximize. So we're just going to change this minimize to a maximize. And to do that, we just flip the signs. So right now we have little m equals this, big M equals negative little m. So we have to maximize. Our objective function is now negative 2x1 minus 3x2 minus 3x3. So we just flip these signs. So I multiplied it by negative 1. For purposes of putting it in the matrix later, we want it to be equal to 0. So like we want the m to be on the same side as our variables. So we have adding these guys over. We have 2x1 plus 3x2 plus 3x3 plus m equals 0. And I'll come back to that later. And then looking at the constraints, to maximize, we want the constraints to all be less than or equal to. So we see that these first two are not less than or equal to, they're greater than or equal to. So to change that, we flip the signs. So our first constraint, we have x1 minus 2x2 is greater than or equal to negative 8. That's a no-no. We want to maximize. So we just multiply the whole thing by negative 1. And we get negative x1 plus 2x2 is less than or equal to 8. That's what we need. So that's good now. So less than or equal to, we can use it. Going on to our second constraint, we originally had 2x2 plus x3 is greater than or equal to 15. Flip those signs to make it a less than or equal to, and we get negative 2x2 minus x3 is less than or equal to negative 15. And then our third constraint, it's already less than or equal to. Beautiful. We can use it. It's canonical. Canonical. Now we can make a matrix. We're going to just put our constraints here. So we have x1 through x3 within our constraints. So our first constraint is negative x1 plus 2x2 is less than or equal to 8. So we put that here, negative 1, 2, 0, because there is no x3, equals 8. And then our second constraint is negative 2x2 minus x3 less than or equal to negative 15. There's no x1, so that's going to be 0. Negative 2, negative 1 equals negative 15. And then our last one is 2x1 minus x2 plus x3 less than or equal to 25. So we have 2, negative 1, 1, 25. These are just the coefficients of our constraints. And now you see we have these slack variables here, because this is the simplex method. We need slack variables to be able to optimize. And to figure out how many slack variables you need, it's just going to be equal to the number of constraints. So we had 3 constraints, 1, 2, 3. So we're going to have 3 slack variables, 1, 2, 3. And then we also add in our objective function. So our objective function up here made it easier to put it into the matrix. So we have 2x1 plus 3x2 plus 3x3 plus m equals 0. So just taking those coefficients, we have 2, 3, 3, and then 1, 0. So that's our matrix that we've set up from our objective function and from our constraints. And at this step, we have these 3 pivots here. x4, x5, and x6 are our pivots right now, with x1, x2, and x3 being held equal to 0. And so we have x4 is equal to 8, x5 is equal to negative 15, and x6 is equal to 25, so that m equals 0. But x5 equals negative 15 is not feasible. we don't like this negative 15 right here. So we need to choose a new pivot from x1, x2, or x3. So we need to figure out which of these we know already that's going to be in this row because of this negative 15. We want to get rid of that. So that's the row we're going to be working on. But we have to figure out which of these it's going to be. Is it going to be x1, x2, or x3? Which of those is our new pivot column? And we do that by dividing each of them, dividing negative 15 by each of them, and then selecting the greatest one. And so obviously we can't divide by 0, so x1 is out. So it's between x2 and x3. And negative 15 divided by negative 2 is about 7.5, and negative 15 divided by negative 1 is 15. So 15 is greater than 15 over 2. So this is going to be our new pivot. So x3 is our new pivot column. So we're just going to make that a 1, a positive 1, and then 0 out the rest of the column using our row operations. So this is the new matrix that we have, and we see it's no longer any negatives. So these are feasible now. But we've now run into the problem that there's a negative in our last row, and we don't like that. We don't like that negative 3. So x2 will become our next new pivot column. We're just gonna pretty much repeat this process until there's no more negatives here. And then whatever is here will be our final answer. So yeah, we cannot have any negatives in that last row. So this is our new pivot column. But we gotta decide which of these is gonna be our new pivot. Once again, we come over to the side here and we're gonna divide these by our options. But if we see a negative here, we're gonna ignore that. Negative 3, any negative numbers as options are not gonna be our pivots in this case. So 8 divided by 2 equals 4, and then 15 divided by 2 equals 7.5. For this time, because we're going here, we're choosing the smallest. Whenever you're going this way, we're choosing the largest. Going this way, we're choosing the smallest. So 4 is less than 7.5, so 2 right here is going to be our next pivot. So we're going to make this a 1 and then 0 out the rest of the column. Using row operations, this is what we get. We see positives here, no negatives here. It's okay that this is a negative, because remember in the beginning how we flipped the sign by multiplying it by negative 1? We need to flip the sign back, because we flipped the sign to maximize because we only know how to maximize. But the problem was asking us to minimize. So we just have to flip the sign back. So it's okay that this is a negative right here, because in the end, it's not going to be. Because right now, this is big M equals negative 33. Because what we have is x2, x3, and x6 are our pivots. So we make x1, x4, and x5 equal to 0. x1 equals x4 equals x5 equals 0. So that x2 equals 4, x3 equals 7, and then x6 equals 22. And with these equaling 0, we have that big M equals negative 33, but we want little m. So we just flip the sign back. Big M equals negative 33, meaning little m equals 33. So we have minimized our objective function subject to those constraints using the simplex method. We have m equals 33 when x2 equals 4, x3 equals 7, and x6 equals 22, with x1 equals x4 equals x5 equals 0. We can again see that from here. This zeroes out, this 0, so that x2 equals 4, x3 equals 7, and x6 equals 22, making little m equal to positive 33. So that's our final answer right there. We have minimized using the simplex method. And we can just do a quick little check if we want. I took our original objective. This was before we flipped the signs to be able to maximize. So this is little m equals 2x1 plus 3x2 plus 3x3. Plugging in x1, x2, and x3. x1 equals 0, x2 equals 4, x3 equals 7. We get 2 times 0 plus 3 times 4 plus 3 times 7. So that m equals 0 plus 12 plus 21, which equals 33. So that's just like a quick little check we can do. So yeah, That's minimizing the objective function subject to the three constraints, well, four constraints, using the simplex method. So those were the three problems. I hope those were helpful, and I hope you have a great day.